Okay, so this is chapter 3.1 through 3.3 on vector addition. This will be the first part. So first thing is, what is exactly a vector addition? So remember that a vector is both a measurement that includes a magnitude and direction. So first of all, you need to know what magnitude is. We have gone over in class on Monday, and we define what magnitude is, and we know what direction is. So there are some examples of what vectors are. A few might be like displacement, velocity, acceleration, momentum, forces, electric and magnetic fields, to name basically a few, but there are also others. Many of them can be represented as vectors, as long as they include a magnitude and a direction. Now, going back to what magnitude is, a magnitude is the measurement, the amount of a measurement. So if you have a measurement and a direction, then you have a vector. Now, vector addition helps us understand how the vectors interact with one another. So if we are going to analyze a vector, that's basically what we're trying to do. We're adding the vectors together. When I say add, I'm basically saying combining the vectors in such a form so that they can help us find an answer. Okay, so having a pretty good understanding of the basic vector analysis and vector addition earlier on, it will help you in your study of physics much later. Okay, so here's a very simple vector addition. If you have a bullet train moving at about 100 miles per hour, and that's just moving forward down the track, and a passenger is walking towards the front of the train at 2 miles per hour, what is the speed of the passenger relative to the train station directly outside the train as it passes? So what would you do? Okay, so basically, the answer is pretty easy. We've done this before, and this is essentially like a relative motion problem. The answer is 102 miles per hour. So really just add the vectors together. So it's pretty easy when the two vectors, like the bullet train and the passenger, are moving along in the same direction. But when they are not moving in the same direction, then it becomes a little more complicated because you can't simply quote unquote add the vectors together because it will require additional steps. So now a more complicated motion will result in something like a two-dimensional motion, as it is more complex because we now have multiple directions. So then this object in red, it starts from the point of origin right over here, and it's moving diagonally. So when we look at this diagonal line, we could say that it's originally here, and it went, say, north, and then it turned east. Okay, north and then east. And so as a result, the red line is the displacement of this object. It started off here at the point of origin and it ended up over here at the end of its path. So then that means we both know that the motion of this object is both in the y direction and the x direction, and by adding the two together, quote unquote, add them together, the resulting motion is this diagonal red line. So if you notice the point of origin and how the arrows meet up over here. When the arrows meet, that means the components, they are going to end up at that location. So we will actually add up the x's and the y's, and then we make a right triangle to form this right triangle, and we can use this right triangle to determine the displacement. Okay, so there are some rules. Okay, so the rules are that vectors are generally represented by arrows, as you can remember from the previous slide. The length of the arrows represents the magnitude of the measurement, so it should be drawn relatively to scale. Okay, like for example, if you have something that's 10 meters long and you want to scale it down, you want to scale it down to maybe 10 millimeters or 10 centimeters long or something like that, just so you have a 10 to 1 ratio or 1 to 10 ratio of the scale. So then another arrow, let's say it's 5 meters long, and you scale it down, it should be 5 millimeters or 5 centimeters long, and that should be drawn to scale or half the length of what you have originally drawn. So that way, that scaling will be better represented by the actual motion of the object. And the arrowhead will indicate the direction. Whatever direction that the arrowhead is pointing in is the direction in which this object is moving in on your paper. Okay. Now these vectors are quote unquote movable because you could very easily rearrange multiple vectors to analyze them simply. okay, more simply. And so then as you arrange them in a certain way, the resultant will still be the same as long as you follow the next rule, that you follow the head to tail rule. That means the head to tail rule ultimately means that if you have to move the arrows, you have to connect the arrows together from the point of the vector, the tip of the arrow point, to the end of the next vector arrow, so the butt end of the arrow. So head to tail rule. So when you're doing this, you got to remember you shouldn't change the length of the arrows or the direction of the arrows. You're simply just moving them side to side, and we'll kind of deal with that in a little bit later. Okay. So these are the rules. You want to write them down, pause them, make sense of it, summarize it. You should probably do that. Now, when you're moving vectors, if you let's just say you have these two vectors here, you see how you got vector 1 that's pointing diagonally up, and you got vector 2 pointing diagonally down. This first vector appears to be in the first quadrant, so to speak, and this arrow down here will be in the fourth quadrant. You could move this bottom arrow this way, and by doing so, you now have this pathway of the object moving in this direction and then kind of diagonally down. So the resultant would be from the point of origin to the head, the point of the very last arrow. And by doing so, you now have identified the resultant. Okay? So you complete the triangle, the resultant vector. So then the head of the resultant meets the free head of the vector that we had just moved. So then you now have this line right here represented by this darker purplish line called the resultant. Okay? So that's how you go about doing that. Now, there are a couple of ways to determine the magnitude and direction of your vector addition problems. One way is the graphic determination, and so we'll be doing this tomorrow in class on Tuesday in the lab. So basically, you will follow the path or the directions given about the moving object, and being careful as to follow the actual distance traveled, and or you can draw a scaled distance on a piece of paper using compass directions or a protractor to determine the angle. So then draw the line on the surface to represent the path taken by the object, and after all the paths has been followed and connected using the head to tail rule, measure the distance from the point of origin to the ending position, the free point of the arrow on the very last vector arrow that you have drawn. That distance from the point of origin to the final position will be the magnitude of the resultant, or the magnitude of the displacement in this case. And then you will measure with a compass or a protractor to determine the angle indicating the direction of that resultant. And so since you have now measured the distance, you have measured the magnitude, you have a vector for the resultant. So that's the first method. The second method is the numeric determination, how you use numbers, how you use math to determine that. So first you have to establish a coordinate system to determine which direction is positive and which direction is negative. Then you will construct an XY table like you would to plot a graph. So then for each motion of the object's path, so you will then break down that motion, that vector motion, in terms of an X or a Y. And we can definitely do that in class so you have a better understanding of how to do that. So once you have done that, you will now have a list of all the X's and all the Y's. And so after you're done that, you will then take the sum of all the X values and the Y values, getting a sum total of the X. Keeping in mind that your X's and your Y's could move in a positive or negative direction, so those signage must be included in your XY table. So after you have the sum of the X and the sum of the Y, construct a right triangle. Once you have constructed right triangles, connect the point of origin to the free arrow point, and that will be your resultant. And so you can use the Pythagorean theorem or SOHCAHTOA to determine both the magnitude and direction of the resultant, so that you will now have a number. Now, if you've done this correctly, your graphic representation and your numeric representation of this vector addition problem should be pretty much the same. Okay? So the equations here, and you probably have seen this in class, is located right over here. Okay? get to know them a little bit better, and so you should be able to utilize these equations. All right. Now, how you will determine direction, we sort of talked about this in class as well. You will first establish a coordinate system where if you're going to use a unit circle, the middle part right here will be your point of origin, and all your angles and stuff will then be done in terms of 0 degrees from the positive x or the east direction, and you're moving a counterclockwise direction, moving so will give you the angles and thereby giving you a direction. If you decide to use a compass rose, or the compass rose is pretty much the only determining factor for direction, north, south, east, and west. Okay? If it's exactly between north and east, we call it northeast, which is exactly halfway between 0 and 90 degrees. Same thing with northwest, southwest, and southeast. Now, when you are going to look at some angles, like let's just say it's not exactly northeast, and it's something like 30 degrees. Now, 30 degrees for that could mean somewhere here. 30 degrees could be somewhere here. 30 degrees could be somewhere here, or anywhere along any one of the 4 quadrants. So how are we going to determine that? Because there are literally many, depending on which quadrant you look at, 2 different 30 degrees, right? One closer to the east, or the positive x, and a 30 degrees that's closer to the positive y. So then we have a kind of a confusion, ambiguity. So what we are going to try to do is then, using compass direction, we can say 30 degrees, and you see how if I draw 30 degrees, this will be 30 degrees to the north of the east, because since we're looking at this 30 degrees here. Okay, so this 30 degrees is to the north, or northward of east line. If I want to look at 30 degrees here, it'd be 30 degrees to the west of north, or westward of north. So using our north line as our point of relevance, so then this is our reference point, this north line is our reference point, then that line 30 will be 30 degrees to the east of north, okay? So then you can basically judge on that. It takes a little bit of practice, but really you just got to determine the proper wording. So then if you're going to calculate some things, if you look at this, if our point of origin is right here and you're moving north 10 kilometers and then west 5 kilometers, calculate for your resultant, its magnitude, and its theta, its direction. Okay? And whatever theta is going to be some angle to the west of north. Since we're using this angle is measuring this resultant red line and this 10 kilometers north line. So then that angle right here is our angle to the west of our north line. And now practice B, basically 30 kilometers west and then 40 kilometers south. So our resultant angle is right over here, this angle right over here. And so what is that angle relative to the west is? Okay, so if that's some angle south of west, okay? So go ahead and calculate the 2 r's and the angles and write the direction down correctly. Now the next slide deals with different ways of looking at this problem. Now if you look at this, we got to calculate the angles. Now assuming that this is exactly 45 degrees from the horizontal or 45 degrees from the vertical, same thing with this and this and this, you should have a pretty good determination of how to do this. Alright, so go ahead and put the vectors together. Remember, you are able to move them however you want, draw them to scale on your paper, and try to get them down so that you have a triangle with the resultant forming the last side of the triangle. Okay, go ahead and try to solve for these, and if you have any questions, don't forget to ask them in class.